This is part 5 of the Chapter 2 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. So with this, we've reached the end of Chapter 2 in the book. Now all that remains is to review an example which is presented. This example is presented mathematically, line by line, so what I'll do is explain the math as I understand it, and I hope that I can add value in that way. And before getting into that, we're going to look at what's being done, what the objective is, why this is being done. So what we're looking at here is Principal Components Analysis, or PCA. And I'll start off by pointing out that PCA is somewhat of an umbrella term, which actually encompasses many things. In this video, I'm going to stick to the example presented in the Deep Learning book, but in a follow-up video, I'll take a more generalized look at the PCA and try and unpack it a little bit more. So here at the end of Chapter 2 in the Deep Learning book, PCA is presented as a simple machine learning algorithm, and it can be constructed using only linear algebra principles. For the purposes of this example, the motivation of this algorithm is to compress data. The compression is to be lossy by design, so the goal is to reduce the memory required to store data points while accepting some minimal loss in the data precision or fidelity. The example that we're reviewing shows how you can achieve this goal using linear algebra to reduce the dimensionality of the data. The core of the idea is that if you have data as points in space, then the only way to compress that is to lose some of the dimensions which describe those data points. So that's our premise. We have a collection of m points in n-dimensional space. So for an example, we're going to use two-dimensional space. The way that this will be done will be to transform each point into a codified data point in a lower dimensional space. So what we need is an encoding function that takes in a data point and returns a different point in lower dimensional space. And to supplement that, we need a decoding function, which will take in the encoded data point and return an output, which should be as close as possible to the original input. So with this kind of setup, the outcome is that instead of storing, for example, a gigabyte of data, we could instead store 850 megabytes or whatever the case may be. And the encoding and decoding functions would also be in storage. But the storage of those is relatively trivial compared to how much data we compress. So we have a modest loss in data accuracy, which inevitably accompanies the compression, which is desirable. So as I mentioned earlier, PCA in fact comes in many different forms, and the authors specify that it is defined by the choice of decoding function. In this example, we'll use matrix multiplication as the decoding function. As such, our decoding function G, will look like something that we see here, a matrix multiplied by a codified data point. So G of C is equal to some matrix D times vector C. So from principles of algebra, we can interpret what's going on here as a projection of a data point onto a lower dimensional space to compress it, and then a projection back onto a higher dimensional space to decompress it. This should remind you of the pseudo-inverse video I uploaded if you're following along. So following from that interpretation of matrices as transformations, the column vectors of the transformation matrix can be interpreted as the basis to which a data point is being converted. So I'll do a quick example here to show what this looks like when you evaluate it mathematically. So fundamentally, we want to reduce the dimensions of our data. That means that instead of storing the x-y pair for each data point, we store only one number to tell us where each data point is. In our example, the data space is two-dimensional, so the only way to reduce it is to go one-dimensional, because we can't have 0 dimensions. But keep in mind that if our data space was n-dimensional, we would have more choice as to how to compress it. We could compress it more or less by deciding how many dimensions our encoding space has. Again, in this case, because our data space is two-dimensional, my encoding space is limited to being one dimension. If my data space was 5 dimensions, then my encoding space could be 4, or it could be 3, or it could be 2 dimensions, or it could be one-dimensional. And each of those would correspond with increasing compression, increasing error in the data. Another thing to note here is that this presentation probably brings linear regression to mind. That's because linear regression is actually a use case of performing this kind of analysis on two-dimensional data. But again, keep in mind that if our data was three-dimensional, we could compress it onto a two-dimensional plane instead of a one-dimensional line. So I would suggest you keep playing around with that idea and have a sense of how this works for all dimensions while we see a visual example in this dimension. So again, we want to compress our data by reducing it from 2 dimensions to 1. There are two questions that become apparent simultaneously. The first is that if we're boiling the vector down to a single number, we must ask along what number line, that is, in what dimension. In this context, you could think of the number line as existing in 2D space, although normally we just think of it as one-dimensional. The direction of this number line in space is the dimension we choose to compress onto. It essentially encapsulates the encoding and decoding function that we store in addition to the compressed data. So when we talk about reducing from 2 dimensions to 1 dimension, for example, that doesn't mean just ignoring, for example, the y coordinate and compressing everything onto the x. The idea is that the basis that we choose, the lower dimensional basis, does not need to be the same basis as it does not need to be a subset of the basis that we are working with in higher dimensions. So in 2 dimensions we have x and y as our bases, vector I, unit vector j. But when we compress that to 1 dimension, we choose what direction that dimension will be going. So that's represented by the yellow arrows here. And you can imagine that the yellow arrow would have high error characteristic to it if it were simply along the axis. So that's the idea of how we can change our axis, change our basis to reduce error while reducing dimensionality. So as I mentioned, there were first 2 questions that become apparent. So that's the first, what number line, what dimension do we select? And the second is to ask, what single value should each point correspond to on that number line? That is, how do we encode the data? If we're being mathematically rigorous, we have to prove that once we've chosen a basis for compression, the means by which we map each data point onto that basis is the optimal way to minimize error for each data point. Fortunately, geometry tells us that the way to do this is obviously to project data onto the basis, so that the codified data point is going to be the point on the line nearest to the actual data point. And that way we can be sure that error is minimized. And we can see this visually as the error vector from each data point to its encoded point meets the basis at a right angle. But like I mentioned, mathematical rigor needs to be more than just a visual intuition. So we will prove it algebraically in this example too. So what we're seeing here is the same data plot using 2 different bases as the space onto which data is being compressed. And at the bottom right we can see that the basis on the right gives us less error. So that's the better choice out of these 2. Now that we have the visual to accompany this problem, we can take the mathematical perspective to see what data compression really looks like in this scenario. To do this, let's just look at one data point from the previous example to start. It's at coordinates x2 and y equals 1. So we're taking the optimal basis from the selection from the last slide, just from those 2, it's the one on the right. So this one points in the direction of the coordinate x1, y1. So we have a line going at 45 degrees, and we're just saying that's what we're going to compress onto. That's our basis. But it's not guaranteed to be optimal. We're just using it as an example. So understanding that the basis onto which we are projecting forms the columns of our transformation matrix, we can construct a transformation matrix out of our one basis vector. First, we need to ensure that we're working with a unit vector. That's because if we don't use a unit vector, the resulting encoded point will not be the one that's connected to the unencoded data point by a perpendicular line. Instead, it will be somewhere further up or down the dimension we choose, the number line we choose. And so, in that sense, we'll be skewing our encoding by changing the magnitude of the encoded value. So that's why we need to normalize our basis vector to a magnitude of 1, so that the dot product just maintains the magnitude, maintains the 90-degree projection, perpendicular projection onto the basis. So that's computed on the right side. The result of the simple dot product simplified to the square root of 2 times 1.5. Now that we've computed that, we can see how the dimensionality of the data has been reduced in the table at the bottom left. So instead of storing 2 coordinates for each data point, we store 1, and that's the distance at which it lies along the number line laid across the new basis. So again, what this means is that we took our transformation matrix, which was just the unit vector in the dimension of our basis, and we multiplied our data point by that, which really means we were projecting the data point onto our basis. And since our basis was a unit vector, that yields the magnitude of the vector along that basis, which is our encoded data point for that original data point. So if we look at the bottom left, we see the comparison of how much data is being stored. So instead of storing 2 coordinates for each data point, we only have to store 1, and that's the distance at which the encoded point lies along the number line laid across the new basis. The caveat is that a fixed amount of memory is required to store the function we use to compress and decompress the data. In this case, that's just a matrix containing 2 numbers, so I use the number 2 in the example. But depending on how many dimensions we work with in our problem, that could be different. And if we're working on a very large dimensional problem, that matrix itself, that transformation matrix, might be able to be compressed in the event that it follows a pattern or something like that. In any case, in the bottom row of the table, you can see that compression would save us data so long as the total data stored in an uncompressed state is greater than the data stored in a compressed state. The implication is that for sufficiently few data points, such as if we only had 1 in this case, the fixed memory cost of storing the compression function would actually result in having to use more memory than using the uncompressed form. But this is a trivial case because, of course, we'd only be interested in using compression on large data sets where it's going to be helpful. So finally, on the bottom right side, we can see how the encoded data can be decoded by multiplying by the transformation again. Mathematically, we can see that we're multiplying a vector, which is our basis, by a scalar, which brings it to become the representation for our original data vector x. Really, though, we can consider this as a transformation of our one-dimensional encoded point onto two-dimensional space. The reason for that is because if we are working with higher dimensional data, our encoded data itself could be higher dimensional, in which case this process would in fact be a transformation back into a higher dimensional space. So whereas in this case it looks like we're just multiplying our basis by a scalar, really more abstractly we're projecting our encoded point, in this case a scalar, onto a higher dimensional space. So if we analyze this visually, what we're doing is looking at our basis and traveling a distance equal to our code value along that vector direction, as if it were a number line. Then we're decomposing that into the original basis vectors, the x and y coordinates. So we end up with a reconstructed data point in the same coordinate system as our original data point. But of course the reconstructed data point lies on the dimension we defined to be the basis, so it necessarily does not lie on the original data point, and so the difference between these is the error which arises from compression. What the example we'll look at shows is how we can select our basis so as to minimize the total error which arises from consideration of all data points. So of course what I mean by that is that we can have error as 0 in this example. It would be trivial, you just need to select a basis that goes through the data point. But the problem is that we have many data points and there's no straight line that goes between them all. So that's the idea there, to select a basis that minimizes the total error across consideration of all data points. So before we get into that, I'll just also point out that we can see even in this example that the error vector is perpendicular to the basis vector, since its slope is the negative reciprocal of the basis vector slope. But as mentioned earlier, that wouldn't have been the case if the basis vector wasn't of size 1, magnitude 1, as then the decoded data point would have been stretched in a sense. So now we've seen the premise of the method mathematically and visually. The idea is that we can compress data we have by looking at fewer dimensions than those that are given. but that we will introduce some error in doing so. And one way to go about doing this is with matrix multiplication. The missing piece is how we can go about computing precisely which transformation matrix will minimize our error, and that comes from determining what conceivable smaller dimensional basis encapsulates the most variation in the data. So while everything I did so far is a presentation of my understanding of this method, what follows is the algebraic proof that's given in the deep learning book, and I'm going to review that step by step, hopefully supplementing by explaining each change that gets made along the way. So, to proceed and find the solution, we first need to impose some constraints. These are as follows. First of all, consider that we're trying to essentially come up with an alternative basis for our data. The basis of a coordinate system are the foundational vectors, which serve as building blocks to make any other vector in that coordinate system space. For any dimensional space, there are infinite possible coordinate bases. That's not good for our process of trying to pin one down mathematically, so we start off by constraining that solution space by imposing the condition that the columns of D must be orthogonal to each other. Another reason we want to do this is to be able to consider our vectors as truly being independent of one another. This has to do with the whole purpose of the method, principal component analysis, is about finding which basis vectors are the principal components of data. In terms of analysis, it's better for us if these components are as distinct from one another as possible, so that changes on one vector dimension have no impact on another. This is achieved by only looking at orthogonal bases. There's still a problem though, because even if you define and consider two orthogonal directions, there are infinite vectors that could fit the bill as bases in those directions, based on all the possible lengths of vectors you could look at. But we need to pick one to actually construct our matrix. For the same reasons we discussed previously about unstretched projections, we add the constraint that the vector is of magnitude 1. It's a unit vector. So having developed a bit of an idea, our problem statement has become, what lower dimensional or orthonormal basis can I project my data onto, so that after I decompress it, I have maximum data fidelity. Now finally, let's get into the math. The first step is to determine how to compress the data optimally. This bears some resemblance to what I discussed in the second last video, with how the pseudo-inverse could be used to project onto a lower dimensional subspace, yielding minimal error. And again, this is simply a proof for what we understood visually, that if we're reducing dimensionality, the optimal encoding is the one that orthogonally projects our data point onto our encoding subspace. In this case, we seek out how to do that by following through on a statement constructed from our first principles. So the position we take is that C star is our optimal compressed data point, and that's simply equal to the argument C, which minimizes the error function, that being the difference between the original data point and the reconstructed data point. And since these are vectors in space, these are points in space rather, they're vectors, the difference between them is also a vector, so its magnitude is computed using a vector norm. So far, this equation is just stating the obvious. It's a mathematical expression of the premise we laid out, but we can use it to go further. So moving on, the function for minimization can be expanded into these two vectors being multiplied, as we see in equation 2. So that's the transpose of x minus g of c multiplied by x minus g of c. This is just a different way of expressing the Euclidean norm. The Euclidean norm is like taking the sum of each element of a vector squared. So it's the same as having the vector take the dot product with itself, which is mathematically equal to having it multiplied by its own transpose. So again, we can ditch the norm notation because it's mathematically equivalent to the dot product expression, which is equivalent to the vector transpose multiplied by itself. From there, the key thing is that the distributive property can be used to represent this formulation. So the terms are treated almost as if they were constants, yielding this kind of polynomial looking expression of vector expressions. That's equation 3. So from here, the thing to note is that the dot product actually yields a scalar value, and the transpose of a scalar is equal to itself. What that means is that we can take one of the two terms in the middle of the sequence and take its transpose without adjusting anything else in the system, as doing so will just maintain its equality. It will be equivalent. Then we can add them together, those two central terms, to simplify, making the coefficient of 2. So that's what we see in the next equation, equation 4. So recall that the objective was to determine what the optimal argument C, the compressed data point to minimize error after decompression, is. So based on this, the first term, which is not a function of C, can be dropped as it has no bearing on the outcome. So that takes us to equation 5. At this point, we can push further and look for a solution by substituting in the definition we made for the decompression function, g of C is equal to a matrix D times C. So this creates a term on the right which can be evaluated. The transpose of a matrix product is the product in reverse order of each constituent matrix. So that's what happens from equations 6 to 7. Since we define D as being an orthonormal matrix, its transpose is its inverse, and so the term on the right can be simplified to the identity matrix. Well, one key thing to note is that it's only the left inverse, so that's why this works, and I discussed that last video again. At this point, the function can't be simplified further, so vector calculus has to be used to find the minimum of the function with respect to the C vector. We use the typical strategy, which is to find where the derivative equals 0, as that point is the global minimum. So this is high school grade 12 calculus. I won't go into the vector calculus right now, going in depth on the characteristics and definitions of computation of vector derivatives, but suffice to say that in this case we can consider it as analogous to non-vector functions. What I mean by that is that the term on the left can be considered almost like a coefficient of the vector C, and the term on the right as C squared. So the derivative is just the coefficient on the left and 2 times C on the right. But note that for the term on the left, D and X were switched around. Again, not precise, but I don't want to go into the details of vector calculus and derivation right now. So by setting the derivative equal to 0 to find the global minimum, we can isolate for C by moving it over to the other side of the equation and dividing both sides by 2. So we end up with that C, optimal C, to minimize error, given a decoding function d times x is equal to d transpose times x. So note that the implicit assumption here is that the function is characterized by one global minimum, and that might not necessarily be true for a function. So what we've done here really is algebraically prove that if we posit a matrix D with orthonormal column space as the decoding function for an encoded data point, then the code values which, when decoded, yield the minimum error are the code values created by transforming the data point x using the matrix D transpose. Again, what we've really just done here is proved that the projection yields the smallest error. Moving on, so we can put some facts together. We have an encoding function, which is multiplication with the transpose of an orthonormal but overdetermined matrix. Then a decoding function, which is the multiplication of the encoded data with the non-transposed version of that same matrix. So we can combine these processes together to create the reconstruction function, which tells us what the compressed counterpart for any data point will be. What's important to realize here is that D times D transpose is not the identity matrix, or else the solution would be trivial, and there would be no loss of data because D transpose is the inverse for a square orthonormal matrix. So D by D transpose would yield the identity matrix. The important thing is that in our definition we stated that the matrix D would have some number of columns, basis vectors, less than the original amount. That's why we're reducing dimensionality. At this point, it should sound familiar based on if you've watched the video I made on the singular value decomposition and pseudo-inverse. So our matrix D is truncated to be taller than it is wide. As such, the transpose is its left inverse and not its right inverse. So when we multiply it on the right, as we do, we're not multiplying the identity by the identity, but instead we're projecting onto the column space of D, much as we did with the Moore-Penrose pseudo-inverse method. What I'm getting at is that the reconstruction function we've generated is the definition of the projection matrix for projection to a subspace. So now the question for our principal component analysis method is, where do we actually get the vectors to construct the columns of D? To find the matrix D, we can again use the idea of minimizing error. But the important thing is that we need to consider the error across all data points. So whereas the previous proof confirmed that the straightforward matrix inverse provided the optimal encoding and decoding function for any point, for any matrix, the specific matrix has to be computed to minimize error across all points. So that's because if we attempt to minimize error for a single point, as I mentioned earlier, we can trivially ensure that a given point's error will be 0 by just putting a basis through it. But that will be at the cost of increased error for other points. So the whole total system error won't be minimized. So to compute this, our optimal basis, we'll find a matrix that minimizes the Frobenius norm of the matrix of errors computed over all dimensions and points. So in words, this function shows that we want to minimize the sum of all errors, where a measure of error exists for each dimension for each vector composing the columns of D. And the error for each dimension for each vector is equal to the square of the difference between the vector and the original data point. So to pursue this solution, we can start by considering the case where L equals 1. So that's to say the case where we're maximally compressing our data, reducing it to only one dimension when encoding it. By making this decision, our D matrix is reduced to a single column vector, so the situation is easier to get a handle on. That's what we see in equation 2. And moving forward, keep in mind that the constraints that we had set, that the columns of our decoding matrix are orthonormal, and in this case, or rather in all cases, they must be unit vectors as well. So these constraints are captured in the box statements on the right. Once again, we've created a mathematical statement which encapsulates the truth we desire to achieve. And by manipulating this statement, we'll attempt to determine what values of D would make it true. First, the D transpose by X in the term on the right is a scalar. And that opens up some possibilities for us. If you remember from the previous video on the trace, we had mentioned that a scalar can be transposed without any change to it, without having any changes. So we can do that. We can keep the equation equivalent by taking the transpose of D transpose by X. So we can move it to the left of that term. Now the authors cite this as a cosmetic change, but readers should be familiar with this kind of thing. That's what they say. It's important to understand how you can manipulate the mathematical statements to prove what you need. So from there, another cosmetic change can be made. Since the dot product of two vectors is a scalar, and the transpose of a vector multiplied by another vector performs the same function as a dot product, we can take the transpose of that term we had just moved over, because the transpose of a scalar is equal to itself. So combining these facts, we can change the term on the right, so that is expressed as X transpose by D, which is a scalar, which is then multiplied by D, as we see in equation 4. And this change hasn't changed the substance of the outcome at all. At this point, we can eliminate the clumsy summation notation, which specifies repeating the same computation for all the different data point vectors, by instead implementing a matrix which is composed of all those data point vectors as its columns. So that's in equation 5. From there, another change can be made that makes our expression more flexible. Specifically, the Frobenius norm can be alternatively expressed using the trace operator. And this was reviewed last video. So from this point, the transpose can be evaluated on the left side, and then the matrix distributivity principles can be applied, much as if this were a factored polynomial, yielding the expression with many more distributed terms seen in equation 7. That's on the next page actually. So we can see here that we expressed Frobenius norm as a trace, and then evaluated the transpose, and then distributed the trace, and that's what happens in equation 7. So from there, the characteristics of the trace operator can be used to separate out all these terms and manipulate them individually. So first of all, since we were minimizing the function with respect to d, the first term can be dropped since it does not change with respect to d. It's not relevant. Then the middle two terms can actually be considered as equivalent thanks to the property of the trace that the constituents of a trace function on multiplied matrices can be cycled. Then the two central terms in our polynomial-looking function can be added together, creating equation 9. Then the cycling property can be used again on the last trace term to express it in a different form, where d transpose is being multiplied by d, as seen in equation 10. But according to our premise, this is necessarily equal to the scalar 1, since the vector is a unit vector and its dot product is being taken. So those are removed, and it is simplified again to become equation 11. This reveals these two terms to be equal to each other, so we can simplify by adding their coefficients. Since there's a negative coefficient for this term, we can change the objective to maximize the positive term. And that brings us to equation 12. Finally, using the cyclic property of the trace once more, the format can be changed to have the composite transformation x transpose by x bracketed by d transpose and d. Since this follows the basic scheme of the definition of the eigenvector decomposition, we know the solution for the d vector that maximizes the expression is the eigenvector of x transpose by x, which is characterized by the largest eigenvalue. So you should note that I'm just taking this fact from the literature right now, but I'll review the proof and try to make sense of that in the next video, since this same fact about eigenvector optimality has been used in the video on the SVD as well. My goal is to be comfortable with the whole process, and so I'll be taking a look at that. For now, if it makes sense if accepted axiomatically, so we can proceed with that fact to finalize our solution as being the eigenvector for x transpose by x. And again, this should really be reminding you of the singular value decomposition method if you've seen that video. So that's the solution for what is the first principles component analysis. Hopefully this is drawing a lot of parallels for you if you've seen my video explaining singular value decomposition. The proof we just reviewed shows how restricting the selection of principal components to the eigenvectors with the highest eigenvalues allows us to minimize error. While this proof applies for the first principal component, the generalization is that we can include more columns in our encoding and decoding matrix D to weaken our compression but gain fidelity, and that we should always be including the eigenvectors with the highest eigenvalues to do so, so as to be on the efficient frontier of the sacrifice between compression and data fidelity. Again, this turns out to be very similar to the SVD, and that's because, in a sense, they're encapsulating the same idea. That's just being enacted differently. So in my next video, I'll discuss this further. For now, I'm hoping that my understanding of the process behind this example is sufficient so that I can effectively understand the subject matter moving forward into the book. I'm aiming to be able to follow along with the math and have an intuitive understanding of the process, so I hope these videos could put the audience in the same position. Thanks for watching, and take care.